In this related rates problem, we're going to find different values based on a ladder that is leaning up against a wall that is 25 feet long. And so if here's my wall, here's the ground, here's my ladder, and so this is 25 feet. And the ladder is being moved out at the base at, that's my dx dt. If I call this distance x, and this is my height h, dx dt is equal to 2 feet per second. And so letter A, how fast is the top of the ladder moving down the wall when its base is 7 feet, 15 feet, and 24 feet from the wall? Well, what they're asking there is, how does the top here in blue, how is that changing with time? And so when we start these related rates, we need to look at our initial conditions, and I'm going to find how can I relate h, x, and 25 so that I can find dHdt. And since it's leaning up against a wall, all walls are perpendicular to the floor, and so we have a right triangle, and so we can say that 25 squared is equal to h squared plus x squared. And to get the rates, we're going to take the derivative with respect to time, and that's a rate. So both h and x are changing with respect to time, and so when I take the derivative, I'll get 0 equals 2h dh dt, because again we took the derivative with respect to time, plus 2x dx dt. And so all we're going to do here is solve for dh. That's what we're looking for. So we're going to have dh dt, and that's going to equal, our 2's cancel, and so we'll have negative x over h, that's an x, dx dt. Well, now all we need to do is plug in x, h, and dx dt. They give us 3 different values here. And so when x equals 7, x equals 15, and x equals 24, well, we have a right triangle, so we can use the Pythagorean theorem, but these happen to be triples if the hypotenuse is 25. So if x is 7, h is 24. If x is 15, h is 20. And if x is 24, h is 7. And so we can just plug in these values now. So for when x is 7, that's equals, we'll get negative 7, h is 24, and dx dt is 2, and so we'll get negative 7 over 12 feet per second. And so we can do that with 15 and 20, 24 and 7, and so the other answers, just draw an arrow here, we'll get negative 3 over 2 feet per second, and then negative 48 over 7 feet per second. So depending on how far away the ladder is from the base of the wall, the rate of change of the height of the ladder is changing by these rates when x is 7, x is 15, and x is 24. For letter B, what's going on here? For letter B, right, we're going to talk about the area of the triangle. And so here's my area. And we know area of a triangle is equal to 1/2 my base times my height. And in this case, my base is x, so we get 1/2 x times h. Well, to find how the area is changing with respect to time, we're going to take the derivative with respect to time. And since we know that both of these are changing with respect to time, we're going to use the product rule. And so dA dt will equal 1/2 my first times the derivative of the second, so that's dH dt, plus 1/2 my second times the derivative of the first. And so here, we have how dA and dt are related to dH, dt, and dx, dt. We're looking for it when x is 7 and h will then be 24. And in letter A, we found dH dt at this moment. dH dt is equal to negative 7 over 12. And so we can just plug in these values now. So dA dt will be 1/2, 7, negative 7 over 12, plus 1/2. The height is 24. dx dt is 2. And so when you plug that into a calculator, you will get approximately 21.958 feet squared per second. All right, so that's letter B. On to letter C. So in letter C, there's my wall, here's my ladder. We're looking for how this angle changes, right? So we're looking for d theta dt. And so when we look at our triangle here, we know this is x, h, this is x, and this is 25. So how can we relate theta x h 25? Well, theta will be changing with both x and h, so we would have to use the quotient rule, right, if we relate it with tan theta. But it also just relates with x and 25. This is a constant, so if I can always incorporate a constant, it's going to make our life a little bit easier with differentiating. So sine theta, which is your opposite over adjacent, is x over 25. Backtrack, sine theta is opposite over hypotenuse. Both theta and x change with respect to time, and so we're going to get cosine theta d theta dt from the chain rule equals 1 over dx dt. And so I'm going to solve for d theta dt, and I'll go up here. So d theta dt, that's what we're looking for, is going to be equal to 1 over 25. I'm going to bring over the cosine theta, so 1 over cosine theta times dx dt. And so 1 over cosine theta is secant theta over 25 dx dt. And so let's look at what we have here. Secant theta, which is my hypotenuse over my adjacent. So secant theta is going to be 25 over 24, because when x is 7, h is 24, times 1 over 25 times 2. 25's cancel, and we'll get 1 over 12, and my units here would be radians per second. And so this is how you would complete the moving ladder problem with 3 different cases. The first one being the rate at which the height is changing. The second case, the rate at which the area of the triangle is changing, formed by the wall, the ground, and the ladder. And the last one is how the angle between the ladder and the wall is changing with respect to time.